Hello teacher, my name is Pon Sukkitprasert and today I'm going to simulation the Airfoil video assignment. So first step is we open the workbench and sys and we drag up the free flow frames here and then open the geometry. Okay, now here we have to sketch the airfoil, but we don't know how to sketch in the curve of airfoil, right? So we need to open this website for the coordinate of airfoil and ACA 241 flow. So this is a data file coordinate. We need to copy this and I put it in, command it in ChatGPT. So I put a command prompt like this, convert the two low file into form like this: group index XYZ coordinate and format by resampling 60 point with a cosine spacing. Include only one LE at 0, 0 and 1 TE. Other LE upper TE lower near LE without duplicating. LE TE inward X multiplied by -1 and set all 0 and make 6 decimal. So why does the example use 60 cosine spacing points when using airfoil in CFD or CAD? They typically don't use point directly from the raw file. Instead, we choose a reasonable number points such as 60 or 100, distributing point using cosine space, also known as a cosine clustering. So 60 points cosine spacing, we can choose 60 points to distribute intelligently, then add the head tail smoother. So we wait the ChatGPT to do for us. Okay, then we get it. Let's see if my command is correct. Okay, and then we get this coordinate and we copy it and save in the notepad. And then we get back to our geometry. In the sketch one, we create a 3D curve and then pick from the coordinate file that we save. Right here, open it, and then we get this generated. But this sketch is not complete yet because we need to add another line to fulfill it by, I think, around here, line from point. Okay, and we already complete the sketch of airfoil. Next, we create another sketch. Like a domain of the fluid. Dimension. This one make it 10 meter, and this one is 20 meter long. And then we create a surface from the sketch. Shoot this line and then generate. Wait. Oh, sorry, I need to trim the middle line first. So I go with the modify trim this line first and then here right from sketch generate. No, surface from sketch, sorry. Generate. And then we get a surface domain of the fluid. And then we need to create a airfoil surface too. I think we need to choose surface from edge. And apply. And then we have two surface, but we need this surface to be the whole. So we create the boolean and then subtract. Click the domain fluid, add a tangent target, and pick this surface as a 2 to subtract, generate, and then we already have hole for airfoil. And then we need to divide the domain fluid part to make the mesh easier. So we sketch the particle part line for projection, and then we click the line from sketch. Okay, and then we click projection for divide the domain, and target is our domain generated. And yeah, we already have 4 part. And then don't forget to merge the additional line that we add. So we click merge, change the face to edge, and then we choose this line and that line, apply, generate. Okay, we already merged it. And then don't forget to subtract the line body, so it's not gonna error in the mesh part. Okay, I think we already finished at the geometry part. Okay, next we start doing mesh. Here I'm gonna click generate mesh first for test if it's error or not. Okay, it works. Then we insert fetch meshing. Okay, in this step I apply fetch meshing to generate the structure mesh over the entire 2D flow domain. This is especially useful for airfoil simulation to maintain uniform mesh distribution. And then I am gonna apply the edge sizing. I'm going to apply all the edge first. Four edges. And then try to generate. Okay, nothing happened yet because we didn't set up. Okay, and then I'm going to change to the number of division to 100, which means each selected edge will be divided into 100 mesh segment. Here is also 100, and the last one we we set to 300 for 300 mesh segments, and then capture curve curvature thick select yes to ensure the mesh follows the curved surface of the airfoil accurately, sorry. And then finally we set the bias factor to 10 so that the mesh is finer near the airfoil and coarser farther away. This is improved accuracy in areas with high flow gradient such as near the surface of the airfoil. And the goal rate is set to default 1.2, which control how quickly the mesh will grow in the side away from the boundary. But here, if we notice, this edge is not linear phi to phi. It's phi cos and phi, so we need to reverse the edge here and do the another. Let's try to set no bias first in these two, and then generate. Okay, I think right now the mesh look acceptable. So we need to set in inflation allow the airfoil to make it more element, so it's going to accurate the calculation allow the airfoil because the flow pass through the airfoil and they contact around here. So we set it we set the element phi right here and cos outside. Okay, here it's time to set all the name section. First, this is a airfoil ball. And then we have a outlet on top, outlet on bottom, and then outlet domain on this on bottom. And I need to fix this chain, rename it to on right. Outlet on line, outlet on bottom, yes. And then the last is inlet flow. Inlet flow from here. We set the name section on the domain to allow the program to calculate which direction the wind will come in and which way it come out. And I think that is all for the meshing. Okay, update, and then finish for the mesh. Next is setup step. Double precision and two core. Set off this at the result. And then about the model viscose, we change K omega to Spalat Amalas model. This one is one equation turbulence model widely used for external aerodynamic like Airfoil. It provides good accuracy with low computational cost. And then set everything as a result. Click OK. About the material, we use air, so we don't need to change anything. And cell zone is all. I set the free zone so as air with no frame motion and no source term. The flow is assumed steady in a lap frame. And then the main setting is about the bond boundary. So about the boundary, let's start with the velocity inlet flow from inlet from here. We set the first step, we need to change component to magnitude and direction, so we can adjust the magnitude and adjust the xy direction. So I set it as 1 meter per second as required by the assignment. And right here, since we apply the airfoil to 4-degree angle attack, so I calculate the unit vector by the x is a cos angle cross 4-degree direction, so it's equal to 0.9975, and the y axis is sine 4 angle, so it's equal to 0.0697, and then apply. Next step is we need to change the outlet bottom and the top as velocity inlet, because the fluid domain is large, and using pressure outlet here may cause the unrealistic backflow. These surfaces are not actual outlet of the flow, so if we in the real life, so flow attack here and just curve like this, they are not go out from here. So if we set it outlet here, it may cause the error in the residual in the future. So we need to change it to velocity inlet instead of pressure outlet here too. And then we set it like in the inlet. Apply. So let's check again in the display if it go inlet or not on outlet top and bottom. So here it's inlet now, so it's work. And then about the outlet is a pressure outlet. Gate pressure is set default to 0. Correct. And then airfoil wall, no slip, steady, stationary wall. Okay, standard, correct. Next, we need to specify what we need in the report. So we define definition of the lift and drag. Where do we look? We look at the airfoil wall and then write the name to lift report definition. And then I'm gonna click the report file out because we don't need it. And next, do the same thing as the drag. So we go in force report, click that, and then airfoil wall, dig report file out, and then change the name to drag report definition. Okay, and then next step is monitor residual. So we need to set the program to make it less error and convert. So we need to change absolute criteria right here to 1A 0.000. And in the conversion condition, I create the two report definition, lift and drag. Select them here, and this means that we set the simulation to automatically stop when the change in lift and drag value is less than 1 E 6 O for the 3 consecutive. And after the first 100 iteration, please ensure our results are stable and reliable. And then next is initialize. So before starting the simulation, we need to initialize the solution. Initialization sets the starting value for all variables in the domain, such as velocity and pressure. So I use hybrid initialize, which is more robust and efficient for complex flow field. Without initialize, Fluent won't know where to begin the calculation. So when we finish, and then we go run the calculation. So I'm gonna set the number of iteration to 1000, and then click calculate. While it calculates, we can see the lift and drag report here. Okay, when we finish, it's convert before the integration that we set. We can look at the result of control by the pressure first. This might be correct because the air drag to here, so it have a lot of pressure here, and it flow. We can look at the velocity. It flow to here by 4-degree angle, so it lift up 4 degrees. Next, we look at the value of the force of the lift and drag in report here. So first we look at the drag force. So we need to set the direction like we set in the inlet velocity, cos 4-degree angle and sine 4-degree angle. Okay, we got the coefficient of drag, total coefficient, or CD, equal to 0.04. We record it. Cos drag, and then we change the direction vector to lift. So this is a minus sine 4 angle and cos 4 angle, and we got a coefficient of the total lift right here, or CL. So we record it. And then we can calculate the lift and drag force by this formula. So I put the ChatGPT to calculate for me, and I get this value. Record it. Lift we get 0.2 Newton, and drag we get 0.02 Newton. And next, when we get the value, we need to find the validation by create a new file mesh. So we start with, we create a cell register. We create a region that cover all of the mesh that we all of the geometry that we do. Set it in 1000 to make it all cover. I think like this, and then save. And then we click manual, quick refine mesh criteria, and then adapt. And then right now we have
more file image. And then we initialize and run again. Okay, finish. Convert. Okay. Then we go check the lift and drag coefficient again. And then record. Image. And this drag. This lift, sorry. Lift file image. And then we got the value of the both force, lift and drag in the file mesh. We record it. And then we calculate the error. Here is the percent error. So we do a cosmate, we get the lift 0.2, drag is 0.02, but 5 mate we get 0.3 and 0.021. So we put it into the error formula, and then our conclusion is we get the error of lift 31.68% and drag 15.29%. Thank you for the listening.